Here is the graph y equal to x squared minus 2x plus 1. I'm moving the x around on the x-axis, and notice that it determines a point B on the graph above it. Since any 2 points determine a line, by moving the B around, I can determine lots of different lines that go through the different points B made with A. Notice how the line disappeared when I put the B right on top of A? That's because you need 2 points to determine a line. Now there is a line that is determined by the single point on our graph. We're sneaking up on it with a line that is going to just barely touch the graph exactly at the point A. This is the tangent line to our curve at the point A. Now you would have noticed that by moving the point B around and making the line through the points A and B, we could make lines that were getting very, very, very close to this tangent line. We see that the tangent line at x equal to 2 is the same as the limit line that we get by moving our x's closer and closer to 2. Notice, if I move over horizontally 1 step, then I can move up 2 steps vertically and get right back on to my tangent line. That is exactly saying that the slope of the tangent line should be 2. Now, if we were wanting to compute the slope of the tangent line, we've already noted that the tangent line is a limit of the secant lines. So the slope of the tangent line should be a limit of the slopes of the secant lines. We can use this idea as a means for computing the slopes of any tangent line. So let's work with this example and use some algebra to compute the slope of our specific tangent line at the point x equal to 2. First, let's make sure that we have all the formulas in place that we need. Remember that the graph is given by y equal to x squared minus 2x plus 1. This is the function of x that we're going to be analyzing. A was our point on the graph at x equal to 2. B is our point on the graph that we move around by varying the x coordinate in the vicinity of x equal to 2. The slope of the line through those 2 points is given by the formula below. Let's describe this formula in terms of the function of x that gives us our graph. As we change x, the f of x gives us the y, and the f at 2 is always going to be 1. Remember how we moved our secant lines closer and closer to the positioning of the tangent line by moving the b closer and closer to the a. And this was done by moving the x-coordinates of the b closer and closer to 2. So we need to find the limit as x approaches 2 of our slopes. And I can plug in now for the f of x and start to simplify. Plugging in 2 into our formula gives us the expected 0 over 0, so we have to do what it takes to simplify that. Now, when we plug in 2, and we see that our limit value is 2, just as we had worked out before by looking at the graph. Now there are lots and lots of points on the curve at which we might have a tangent line. And by moving our x around, we can get to each and every one of them. For instance, let's look at the point at x equal to minus 1. Move from A horizontally 1 step and down 4 steps, and you're back on the line. So that means that the slope here is minus 4. To get the slope at x equal to 0, notice that when you go over 1 step horizontally, you go down 2. So the slope at x equal to 0 is negative 2. At x equal to 1, the tangent line is horizontal, so its slope is 0. The slope is 2 at x equal to 2, and the slope at x equal to 3 is 4. It would obviously be nice to have a formula so that at each point which we locate by an x, we can use it to find the slope of the tangent line to the point. It is in fact fairly easy to build such a formula that will tell us the slope of the tangent line at each point given by an x. We still have the same formula as before for our graph. We are going to use x sub 0 to represent the x-coordinate of a fixed point on the graph, and then x will represent the x-coordinate of a nearby point that we will be moving closer and closer to that fixed x sub 0. Now we can find the slope, the line that contains the point at x and the point at x sub 0. In order to find the y and the y0, we now have to plug into our formula for f of x. Now we have some algebra to do. We need to gather together the like powers of x in the numerator, and then I'm going to separate the fraction into two pieces that I can easily reduce. Our formula simplifies to just x plus x sub 0 minus 2. This is a formula for the slope of the secant line that contains the points at x and at x sub 0. In order to find the slope of the tangent line, we're going to need to move the x's closer and closer to x sub 0, and hence we will compute by finding the limit as x approaches x sub 0. We can substitute in the secant slope, x plus x sub 0 minus 2. We obtain that the slope of the tangent line at x sub 0 is given by 2x sub 0 minus 2. We now have an all-purpose formula that can tell us the slope of the tangent line any place on our curve that we like. For example, do you remember when we were looking at the tangent line to the curve at the point x equal to minus 1? We mapped out the slope of that line and got that it was minus 4. Let's try using x equal to minus 1 in the formula that we just built. If we substitute minus 1 for x in our formula, we immediately get minus 4 again. We can find the slope of the tangent line at any point on our curve by using its x-coordinate and substituting it into this magic formula to get the slope. Let's take the example that we were just looking at. Try to make it look like one of the book problems 11 through 14 in section 2.1. These involve two arbitrarily chosen points at x equal to x0 and x equal to x1. Ours will be at x equal to 2 and x equal to 3. They would state the problem for part A as requiring that we find the average rate of change in f over the interval from x0 to x1. This is the same as finding the slope of the secant line through the points at x0 and at x1. At x equal to 2, the point on the graph is the point 2, 1. We get the 1 by plugging into our formula and working it through to get that y is equal to 1. At x equal to 3, the point is 3, 4, and similarly we have to plug into our formula to get y equal to 4. We can now find the slope of the line through the points 2, 1 and 3, 4 and see that that slope is 3. Using function notation, we could have written down the formula for the slope of the secant line this way and then fairly quickly and efficiently gotten to our answer as before. In part B, we would be being asked to find the instantaneous rate of change in f at x equal to x sub 0, in our situation at x equal to 2. This would be the same as the slope of the tangent line to the curve at x equal to 2. We can figure out the slope of the secant line through the points x, y, and 2, 1. Plugging into our familiar formula and then doing some algebra, we get a fairly reasonable formula after a little bit of fussing around. In order to get the instantaneous rate of change, we're going to have to take the limit as x approaches the instant that x is equal to 2. If we just try plugging in x equal to 2, we run into our usual 0 over 0 problem, but we can fairly easily reduce the fraction and find that our limit is going to be 2. Part C would require us to find the instantaneous rate of change in f at an arbitrary x equal to x sub 0. This would be the same as finding the formula for the slope of the tangent line to our curve at any x equal to x sub 0. We figured out this formula already, but I want to quickly reproduce the work that was needed here. We found the slope of the secant line through points xy and x0, y0 on our curve. We plugged x and x0 into our function, put everything in place, started grouping things so that we could break things up into nice fractions that would reduce. Then we took our limit as x goes to x sub 0 in order to get our final formula. Part B was to sketch your curve and then sketch the lines that you would have found the slopes of from both part A and from part B. Here is the secant line from part A that went through the points at x equal to 2 and x equal to 3. Here is my sketch of the tangent line from part B that went through the point at x equal to 2. Notice that in order to know what's really going on here, that one needed to mark in the coordinates of the points of intersection with the curve.